Okay, so announcements. The first chapter 3 homework is due today. The second chapter 3 homework is due in a week. On the day you'll be having the quiz for chapter 3. So the quiz for chapter 3 will be next week on Monday. We're finishing chapter 3 today. And we have a lab on Wednesday. I'll make sure that there's an announcement for it up on Blackboard. I can't recall if I put one up, scheduled one yet. Carolyn? So, part 1 of the first chapter 3 homework is due today. The second chapter 3 homework is due in a week. The chapter 3 quiz will be in a week on Monday. We have a lab on Wednesday. And we will be finishing off chapter 3 today. So, today we're going to talk about momentum. We're going to start with linear momentum. That's momentum in a straight line. So momentum, P is equal to M times V. That's the general definition of momentum. It's mass times velocity. So linear momentum is mass times velocity, and that is velocity with a direction. So the direction matters for momentum. And if we have a system of objects, the total momentum is just the sum of the initial momentums of the individual momentums. So it'll be M1, V1 plus M2, V2 plus dot, dot, dot. Now, the important thing here is that the one property that momentum has that's very useful is that the total momentum for the total, the final momentum equals the initial momentum. So you can think of that as P1 initial plus P2 initial equals P1 final plus P2 final. So the momentums of various bits. So you can have the momentum of one thing changes, but the total momentum of everything stays the same. Momentum is conserved. So in general, when two things interact, the total linear momentum of an isolated system remains the same if there's no external unbalanced force acting on it. So linear momentum is conserved as long as there aren't any external forces. It doesn't change with time. So that's the total momentum. And if there are external forces, if you just increase the size of your system, it'll end up being conserved. So linear momentum for the universe is conserved. But for problems, you can usually reduce it to a system. And it turns out a condition that's very easy to work with, where you can make some assumptions, is that if you have a collision, you have two objects running into each other, you can say, this is happening so fast that we don't have to worry about external forces. So lots of momentum problems will be collisions or two objects flying apart or something like that. So here is an example of conservation of linear momentum for this man and the boat. The initial momentum and the final momentum have to be the same. And the initial momentum is 0 because they started at rest, and then he's jumping off the boat. So the man goes forward, the boat goes backwards. If the man jumps out of the boat, he has momentum in one direction forwards. Therefore, the boat must have momentum in the opposite direction. Their momentums have to cancel out. If you ever start stepped on something that can roll easily or something like that, you'll have experienced this. Or on a floating thing. You go forward, it goes backwards. Now, it's possible to derive momentum from Newton's laws. You don't need to understand this in any detail. But the basic idea is that if you combine Newton's second law with Newton's first law, you can say Newton's third law says force 1 equals minus force 2. So that means mass 1 times acceleration 1 equals mass 2 times acceleration 2. Acceleration times delta t is the change in v. And you can do a little math and end up with, initial momentum equals final momentum. That's just an example. We don't have to go through that. But the basic rule, momentum is a vector, mass times velocity. So it has a sign matters. So here we have a 3-gram bullet traveling at 333 meters per second. What is its momentum? Note that 3 grams is 0.003 kilograms. And momentum is mass times velocity. Yeah. Because momentum has units of kilogram meters per second. Yes, it's 0.999. So 3 grams times 333 meters per second. We'd like it to be in standard units. So 0.003 kilograms times 333 meters per second. So it's 0.99 kilogram meters per second. 999 gram meters per second, but no one uses that unit. The CGS one would be 99,900 grams centimeters per second. But again, we don't use CGS. Here, if we have a 4.5 kilogram ball with a momentum of 900 kilogram meters per second, what is its velocity? So in general, with momentum problems, these are the two kind of calculations you're going to be making a lot of. You're either going to be finding the momentum because you know the mass times the velocity, or you will have worked out what the momentum should be, and then usually you're looking for the velocity because you know the mass. Okay. Uh, 900 divided by 4.5. Name?
Your mind.
So momentum equals mass times velocity. So velocity will be momentum divided by mass. So 900 kilograms divided by 4.5 kilogram meters per second divided by 4.5 kilograms gives you 200 meters per second. So that was linear momentum, mass times velocity. Now we'll do some problems with um, the interaction with conservation of momentum. So momentum is mass times velocity, and the general idea for conservation of momentum is that final momentum equals initial momentum. So for example, if you start with zero momentum and you have two people jumping, if you have two objects separating, the man here will have some positive forward momentum, assuming that way is the positive direction. And so the boat will have some negative momentum to cancel out the forward momentum. Because the total momentum has to remain at zero because momentum is conserved. So if you apply conservation of momentum, if you have, say, two masses with a spring in between them that are suddenly released, when the spring is burned, the two masses will fly apart due to the compressed spring. And if mass one ends up with a velocity of 1.8 meters per second, and mass one is 1 kilogram, mass two is 2 kilograms, and the velocity of mass one is 1.8 meters per second. The question is, what is the velocity of mass two? Now, the first thing you can observe is that initially nothing is moving. If nothing is moving, the total momentum is zero. So given that mass one equals 1 kilogram, mass two is 2 kilograms, velocity one is 1.8 meters per second, and we're looking for velocity two. The final momentum plus the initial, or the final momentum equals the initial momentum, and that equals zero. And the final momentum is going to be the momentum of object one plus the momentum of object two. And that'll equal zero. So if we solve that, momentum one will equal minus momentum two. So mass one times velocity one will equal minus mass two times velocity two. Because again, mass times velocity, we're adding those up, the total has to equal zero. If mass one times velocity one equals minus mass two times velocity two will equal mass one times velocity one minus mass one times velocity one divided by mass two. So minus one times 1.8 divided by two, which will be negative 0.9 meters per second. So this has double the mass, so it ends up with half the velocity in the opposite direction. That's what happens when you start with zero momentum. And this process also explains jet propulsion. So here I have a balloon full of air. When I release the balloon, air will be flung out the back with some momentum. But this starts with zero momentum. So the total momentum has to be zero. So that momentum goes into moving the balloon forward. So fast light air coming out the back equals slower balloon going forward. And then, because it changes direction as it goes through the air, but that's the basic idea. And that's the same principle for jet engines, and rockets and things like that. You could explain it in terms of Newton's third law of linear momentum, in that, the rocket exhaust doesn't weigh very much, but it is going out very fast. So it has a decent amount of momentum, and that momentum is transferred to the rocket, and that's what causes the rocket to fly. Same thing with an airplane. The airplane pushes air behind it, and that, that's a little easier to think about, But basically, a jet engine, it sucks in air and flings it out backwards at a high speed. That causes the jet to travel forward. So the exhaust gas molecules have a very small mass, but a large velocity. The rocket, on the other hand, has a large mass and a smaller velocity, but momentum is conserved. Mass 1 times velocity 1 equals minus mass 2 times velocity 2. So if you have a system that consists of a 1 kilogram mass with a velocity of 3.5 meters per second and a 2 kilogram mass with a velocity of negative 1.75 meters per second, what is the total momentum of this system? So momentum is mass times velocity for each object. The total, we're just going to add them up. And then after the masses collide, because these two masses, if they're on a collision course, what would the total momentum of the system be? So I'll give you a couple minutes to work that out. Yep, you're just going to mass 1 times velocity 1 plus mass 2 times velocity 2. You find the momentum of object 1, you find the momentum of object 2, and you add them together. Well, this is fairly straightforward. Momentum is mass times velocity. So the total momentum will be momentum of 1 plus momentum of 2. So mass 1 times velocity 1 plus mass 2 times velocity 2. So that's 1 kilogram times 3.5 meters per second plus 2 kilograms times negative 1.75 meters per second. And that comes out to 3.5 kilogram meters per second for mass 1 and negative 3.5 kilogram meters per second for mass 2. So the total momentum is 0. And after collision, the total momentum will not change. So after the collision, the total momentum will be 0. Now, several things could happen. So the two objects could collide and stick, and they both individually have a speed of 0. the two objects could collide and bounce, and they might end up with different speeds after they bounce. You know, things like that. I can't tell you exactly what. Though in this case, they might bounce and end up going in opposite directions to where they would. So mass one would be a 1 kilogram mass with a velocity of negative 3.5 meters per second, and mass two would be a 2 kilogram mass with a velocity of positive 1.75 meters per second. But the question doesn't give you enough information to figure out exactly what's happening with the masses. You just know that they would have the same total momentum after they collide, because momentum is conserved. So here's a problem using conservation of momentum. You have a cannon. It starts at rest. The cannon weighs 1,000 kilograms, and it fires a 4.5 kilogram ball at a velocity of 300 meters per second. And the cannon will be flung backwards because of Newton's third law, but also, because of the conservation of momentum. So the question is, the ball and the cannon start at rest, so everything starts not moving. So what is the velocity of the cannon after the ball gets fired? So we can start with the initial momentum. Initial momentum is going to be a momentum of 1 times momentum of 2, and that's fairly straightforward because nothing is moving. So that's going to end up being 0. So again, if things start at rest, the initial momentum is 0. The initial momentum equals the final momentum, which is going to equal mass 1 times velocity 1 final plus mass 2 times velocity 2 final. That will equal 0. So mass 1 times velocity 1 final equals minus mass 2 times velocity 2 final. This here shows up when you start with 0 momentum. So velocity 1 final will equal mass 2 minus mass 2 times velocity 2 final over mass 1. So that's minus 4.5 kilograms times 300 meters per second over 1,000 kilograms, which gives you minus 1.35 meters per second. Here we have a similar problem. Two masses starting at rest. Mass 1 has a mass of 3 kilograms, mass 2 has a mass of 12 kilograms, and they're thrown apart by a spring. After they separate, mass 1 has a velocity of minus 4 meters per second. What is the velocity of mass 2? Just as a reminder, as these start at rest, your initial momentum is 0. Yes. No, it's 1 meter per second. All multiplying and dividing. So 0 equals mass 1 times velocity 1 plus mass 2 times velocity 2. So mass 2 times velocity 2 equals minus mass 1 times velocity 1. So velocity 2 is going to be minus mass 1 times velocity 1 over mass 2, which is the momentum of 2 divided by mass. That is missing a minus sign. So I'm going to quickly fix that. That should have a minus sign there. So that is minus 3 times minus 3 times minus 4 divided by 12. Well, these are both kilograms. Wow, I made typos on this one. And so you get 3 times 4 is 12, minus times minus is plus. 12 divided by 12 is 1. So it is 1 meter per second. Let me put in the units here. And that's all I want to do as example problems. You'll get more practice on this in the lab on Wednesday. If you want to practice more or look at more example problems, when I post the recording, there'll be a copy of the slides as a PowerPoint. There's a bunch of hidden slides. I hid some problems that I thought were unnecessary. So if you want to look at those, they're all there, they're all worked out. But I didn't feel like I should cover them in class because it just felt like it was too much. So That was momentum. Now let's talk about spinning and twisting things. So, torque is the twisting effect caused by one or more forces. When you apply torque to something, you apply a force to make something rotate. The linear momentum of a system can be changed by the introduction of an external unbalanced force. It turns out, as well as linear momentum, there is something called angular momentum. You may have noticed that when something is spinning, it likes to keep spinning. The angular momentum of a system can also be changed by an external unbalanced torque. Now, torque is relatively straightforward to calculate. It turns out, so it's this twisting action that produces rotational motion or a change in rotational motion. So like when you turn your steering wheel, you're applying a force at a radius. So in general, torque involves a force applied at a radius, like with a wrench. When you have a wrench, you apply a force at the length of the wrench, a radius. So torque varies with the length of the lever arm. So you may have noticed if you have a wrench, if you use a bigger wrench, it's easier to turn what you're trying to turn. You can get it tighter or you can get it loose if it's really tight. So as the length of the lever arm is doubled, the torque is doubled. So torque is force times radius. I mean, it's a little more complicated than that. It also depends on the angle between the force and the radius, but that's all you really need to understand. The longer the lever arm, the more torque. The bigger the force, the more torque. So often there's a limit to how much force you can apply because, like, you know, your arms are only so strong. But if you want to get something that's really stuck loose, you can apply more torque by increasing the length of the lever arm. Getting a longer wrench, using a cheater bar to extend the length of the wrench, things like that. So which has more torque? 4 newtons on a lever arm of 0.5 meters or 5 newtons on a lever arm of 0.2 meters? Remember, torque is force times radius. The first one, you think? Yes. Because 4 times 0.5 gives you 2 Newton meters, and 5 times 0.2 gives you 1 Newton meter. Oh yeah, torque is measured in Newton meters, or in imperial or American units, foot pounds. You may have seen that on car advertisements. You know, this car gives you so many foot pounds of torque. That's how much it can spin the wheels, how hard it can spin the wheels. So torque is force times radius. 4 newtons times 0.5 meters is 2 Newton meters. 5 newtons times 0.2 meters is 1 Newton meter. In fact, the second one has half the torque of the first one, even though the force is bigger. Torque is also how scales work, balance beams. We will eventually do a lab about that. The torque one is greater than torque 2. Now, angular momentum is the equivalent of momentum for rotation. Spinny things also have momentum. And the law of conservation of angular momentum is that the angular momentum of an object remains constant if there are no external unbalanced torques, that is a force around an axis, acting on it. Now, the interesting thing about angular momentum, this concerns objects that go in paths around this big fixed point, like a satellite around the Earth. That's the kind of questions we'll have in this, because they're a little easier to work out. But it also covers anything that is spinning. So angular momentum ends up being mass times velocity times radius, if you have an object spinning around a planet. And if angular momentum is conserved, like in an orbit, you'll have mass 1 times velocity 1 times radius 1 equals mass 2 times velocity 2 times radius 2. So L, angular momentum, is mass times velocity times radius. And because it is conserved, you get mass 1, you get L1 equals L2. Mass 1 times velocity 1 times radius 1 equals mass 2 times velocity 2 times radius 2. And the thing here is you can have situations where the angular momentum isn't changing, there's no torques, but your radius is changing, so your velocity changes. So here, if you have something orbiting, say, the sun, it'll go faster when it's closer to the sun and slower when it's further from the sun. Because mass is constant, but as the radius changes, so must the velocity. So when the radius decreases, the velocity must increase. So the mass times velocity times radius equals mass times velocity times radius. And because the mass of the object isn't changing, you end up with radius 1 times velocity 1 equals radius 2 times velocity 2. So in our solar system, the orbits of planets, the orbits of anything orbiting the sun, are a little bit elliptical. So both radius and velocity will vary slightly during a complete orbit. Just check. Okay. So before I do any problems, I will do a demonstration. But the same thing applies for anything that is spinning. If you want to get into the details of it, the calculations have to do with how the mass and the radius, your mass is distributed, but you can generally think about it as the mass is changes, the radius changes. So as a demonstration, I'm sorry this won't be terribly visible to the people online, but I'm definitely not doing that in the space, doing this in the space in between the up as high as I can take it. So, you might want to move that. Yeah. Here I have some masses at a radius. I'm going to apply a torque with my foot to get myself spinning. Going a little faster. So here you see my radius is large, my velocity is not very fast. If I pull them in, my velocity increases. If I bring them out, my velocity decreases. Yes, I just need to speed back up. So I'm starting with a large radius and a not so big velocity. I pull them in, radius gets smaller, velocity increases. I bring them out, radius gets larger, velocity decreases. And now I need to stop. Demonstration is not great on the inner ear. A little bit.
Make a lot more sense.
So the same thing is why ice skaters will pull their arms and legs, will start jumps with their arms and legs out, and they'll pull their arms and legs in because it makes them spin faster. And additionally, like why divers, if they want to do lots of rotations, will tuck their body in. So, and it's something that has to be dealt with. They're saying momentum. So the problems we're going to deal with are like problems of things in orbits, because the math is easier. If you have something with a more irregular mass distribution, it gets more complicated. But here we have a comet. The furthest point from the sun is at 900 million miles, traveling at 6,000 miles per hour. What's its speed at the closest point of 30 million miles away? So mass 1 times velocity 1 times radius 1 equals mass 2 times velocity 2 times radius 2. It's the same comet, so mass 1 equals mass 2. Mass isn't changing. And we're given velocity 2, radius 2, and radius 1, and we're looking for velocity 1. We're given we're given one velocity and both radii, and we're looking for the other velocity. So if we solve this, we get velocity 1 equals velocity 2 times radius 2 over radius 1. So velocity 2 is our initial velocity at the far point. That's 6,000 miles per hour. So that's 6 times 10 to the third miles per hour. 900 million miles is 900 times 10 to the 6 miles. Divided by 30 million miles. So that's 30 times 10 to the 6 miles. Miles cancel. So we're left with miles per hour. The millions cancel. And you will get 6 times 900 divided by 30, which gives you 180 times 10 to the third, which is 180,000 miles per hour, or 1.8 times 10 to the fifth miles per hour. Oh. The 180,000 miles per hour is how fast it is. Now, this is something, the fact that when you have one thing spinning one way, the other way, you have to correct for the angular momentum. Helicopters start with the rotors sitting still on the ground, basically, and they spin up hard. Well, they start with an angular momentum of 0, and then they put a whole bunch of angular momentum into their rotors. So there's a couple ways you can deal with it. For big helicopters, what they do is that you'll notice you got 2 sets of rotors. Those rotors spin in opposite directions. And that keeps the helicopter from spinning. For smaller helicopters, it has that little thing out on the tail that looks like a little rotor. That is to provide a torque to counteract the angular momentum that's being added by spinning the blades on top. If that fan stops working, the body of the helicopter spins opposite the blades on top. And now that's because of that. There's like a trick you can do to land a helicopter if your engine dies, where you counter rotate. But yeah, it's not a pleasant thing to have the body of the helicopter spin opposite. So here is the example of a figure skater. They start their spin with their arms out at one angular velocity, and by pulling in the arms of the skater, they spin faster because the average radial distance of the mass decreases. There's an actual way you would calculate this, which we are not going into, because that is beyond the scope of this class. But you can work out how the distribution of mass changes and the radial, and how the average radial distance of the mass decreases, and how much faster they'll spin. So mass is constant, radius decreases, therefore the velocity increases, so they spin faster. And that velocity is the linear velocity. It's how fast, your hand is moving. And because the radius is smaller, it actually increases the rate that you rotate even more. because you're going faster over a shorter distance because it's a smaller circle that you need to go around. So here's a problem for this. If you have a 0.35 kilogram mass spinning on a half-meter long string, traveling at 5 meters per second, what is its angular momentum? Yes. Did you say 0.87? Yes, it's 0.875, and the units are kilogram meters squared per second. So 0.35 kilograms times 5 meters per second times 0.5 meters, 0.875 kilogram meters squared per second. So here, if you have a spinning 0.5 kilogram mass on a string, and it has a speed of 4.5 meters per second, and an angular momentum of 0.9 kilogram meters squared per second, how long is the string? So if you have a mass spinning around like this, and you know the angular momentum, and you know the mass, and you know the velocity, you want to know how long the string is. Is it 0.4? Okay. It is 0.4 meters. No, it's 0. If it was 9 kilograms, it would be, it's 9 kilogram meters per second squared. Yes, it would be 4, not 0.4. But it's angular momentum is mass times velocity times radius. So radius is angular momentum divided by mass times velocity, which is 9 kilogram meters per second squared divided by 5 kilograms times 4.5 meters per second, which gives you 0.4 meters. And here we have, if you're spinning about a 1.1 kilogram mass on a 0.3 meter string, and the mass travels at 3.6 meters per second, if you shorten the string to 0.2 meters, how fast will the mass be moving? So this one, you're going to have to use this formula. Yes. No. See if I can figure out what you might have done wrong. I'm not sure what you did wrong there. So, angular momentum is mass times velocity times radius. So mass one times velocity one times radius one equals mass two times velocity two times radius two. But the mass isn't changing. Both of the masses are the same mass. So the 1.1 kilograms will cancel out. And you get 3.6 meters per second times 0.3 divided by 0.2. So if you find the total angular momentum, it's 0.108 kilogram meters per second squared divided by 0.2 kilogram meters, and you'll get 5.4 meters per second. So you'll get velocity two is velocity one times radius one over radius two. So 3.6 times 0.3 divided by 0.2 gives you 5.4 meters per second. So here's a similar problem with an object in an orbit. So the only real difference is the numbers are bigger. We have a 3,000 kilogram satellite of Moon with an elliptical orbit. At its closest to Moon, it travels at 3 times 10 to the 5 meters per second, and is 2 times 10 to the 7 meters from the center of Moon. At its furthest from Moon, the satellite is 5 times 10 to the 8th meters away from Moon. So the question is, how fast is it traveling there? So again, angular momentum is conserved. And importantly here, mass will be constant, so it will cancel out. Mass one equals mass two. This is the sort of problem that will be in the case. No, but it's not. No. So velocity two is going to be velocity one times radius one over radius two. That's 3 times 10 to the 5th, times 2 times 10 to the 7th, divided by 5 times 10 to the 8th. The mass cancels out. If you wanted to include the mass, it'd be on both the top and the bottom. So the nice thing about these, usually the mass cancels out. So velocity 2 ends up being 1.2 times 10 to the 4. Yeah, you multiply by the mass. Meters per second, or 12,000 meters per second. Yeah, if you do include the mass, you have to put it on both the top and the bottom. Yeah, in any problem you're gonna get in this class, the mass will cancel. I'm not even sure if I can give you the mass on the problem on the test quiz. I might leave, I can't remember if I leave it out or not. But, like, in general, the mass will cancel out. Because most of the time your mass isn't changing. So that's the end of chapter 3. Here are some important equations. Newton's first law and Newton's second law are covered by force equals mass acceleration. Or if you want to think about weight, weight equals mass times g, the acceleration of gravity. Newton's third law is that the force of one on, if you have two objects applying forces to each other, the force on object 1 will be minus the force on object 2. The forces come in pairs that are equal and opposite. So if I push on the wall will push back on me with equal and opposite force. The force of gravity, the general equation for the force of gravity is big G, which is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. That's just a constant. Times mass 1 times mass 2 divided by the distance between the two objects squared. That is the force between any two objects due to gravity. If you want to find the acceleration due to gravity around some spherical object, it's big G times the mass of that object divided by the radius of that object squared. So that can get you G if you plug in the mass of the Earth and the radius of the Earth. Linear momentum is mass times velocity. The total momentum, the final total momentum equals the final initial momentum. And if the momentum total is 0, mass 1 times velocity 1 equals minus mass 2 times velocity 2. Angular momentum is mass times velocity times radius. So angular momentum 1 is conserved. If it's conserved, angular momentum 1 equals angular momentum 2. So mass 1 times velocity 1 times radius 1 equals mass 2 times velocity 2 times radius 2. Generally, the mass is constant. Mass 1 will equal mass 2. Your mass isn't changing, and that's conservation of angular momentum. And then lastly, torque equals force times radius. And technically, yes, it should be, strictly speaking, if you're being fancy about it, it should be written with a cross, because it's, if you deal with them as vectors, it's the cross product with the vectors. You don't need to worry about that. Just know it's force times radius. I'm pretty sure the torque question is just multiple choice on the quiz of the test. It's just understand that bigger lever arm gives you more torque, and more force gives you more torque. And then in general, force times radius. There's some details having to do with the angles, but you don't need to worry about that. That's chapter 3. Any questions? Well, that's it. The first homework for chapter 3 is due today. The second homework for chapter 3 is due in a week. The quiz will be in a week on Monday, and we have a lab on Wednesday. The lab will be about momentum, so you'll get some practice on it. So I'm gonna stop sharing. And